In May of 2026, scientists at the University of Miami published the results of an analysis of data from 4 mooring arrays along the western boundary of the North Atlantic. The moorings have been operating since 2004. They measure water temperature, salinity, and the velocity of ocean currents. And they recorded the same thing at all 4 latitudes. AMOC is weakening, not from a model, not from indirect indicators, from direct measurements. 20 years of observations and one conclusion. The Atlantic Meridional Overturning circulation, the system of currents that warms Europe, feeds the African monsoons, and regulates global sea levels, is losing strength from 20 sverdrups in 2004 to 15 today. This is not a warning about the future. This is a measurement of the present. And geology tells us exactly what happens when this system stops. Before we go any further, please subscribe to this channel. Your support really helps us to continue this work. Thank you. There is a machine at the bottom of the Atlantic Ocean. You cannot see it. You cannot hear it. It has no moving parts, no fuel source, no operator. It runs entirely on the physics of salt and temperature and gravity, and it has been running with occasional catastrophic interruptions for the better part of several million years. Without it, the climate of northwestern Europe would resemble that of northern Canada at the same latitude. Without it, the monsoon rains that sustain agriculture across a swath of West Africa would weaken or fail. Without it, sea levels along the eastern seaboard of the United States would be significantly higher than they are today, because the machine actively pulls water away from that coastline and toward Europe. It is called the Atlantic Meridional Overturning circulation. Scientists refer to it by its acronym, AMOC. And for most of human history, it has been invisible, undetected, taken entirely for granted, because its effects are so fundamental to the climate system that they register not as anything unusual, but simply as the world. Understanding what AMOC actually is requires understanding the ocean, not as a flat surface, but as a 3-dimensional system in constant motion. The surface of the Atlantic, driven by winds and heated by the sun, moves in patterns that are broadly familiar. The Gulf Stream, which carries warm tropical water northeastward along the American coast and then across toward Europe, is the most famous surface expression of this circulation. But the Gulf Stream is only part of the story, and in some ways, the less important part. What makes AMOC a genuinely planetary-scale machine rather than just a surface current is what happens when that warm, salty water reaches the North Atlantic and begins to cool. As the water of the Gulf Stream extension moves into the higher latitudes of the North Atlantic, into the seas around Iceland, the Labrador Sea, the Norwegian Sea, it loses heat to the cold Arctic atmosphere above it. And as it cools, it becomes denser. Warm water expands. Cold water contracts. But there is a second factor at work alongside temperature, and this one is the key to everything that follows. Salinity. The Gulf Stream waters that arrive in the North Atlantic are not just warm, they are salty. They have been evaporating in the tropical Atlantic for years, losing water to the atmosphere while retaining their dissolved salt. Salt increases density, just as cold does, and the combination of cold and salty in the North Atlantic creates water that is among the densest on the surface of the planet. Dense water sinks. This dense North Atlantic water plunges thousands of feet to the ocean floor and begins moving south as a deep, cold bottom current, spreading eventually across the global ocean floor in a circulation pattern that connects all the world's ocean basins. And as it sinks, it creates a void at the surface, a pressure gradient that pulls more warm surface water northward from the tropics to replace it. That is the circulation. That is the machine. A thermohaline conveyor driven by the fundamental physics of salt and temperature, moving roughly 17 to 20 sverdrup of water. One sverdrup equals 1 million cubic meters per second, through the North Atlantic continuously, transferring an amount of heat energy comparable to 1 million power stations from the tropics to the high latitudes of the Northern Hemisphere. The consequences of this heat transfer for climate are not subtle. Northwestern Europe sits at latitudes that, without AMOC, would be comparable in climate to Labrador or Siberia. London is at roughly the same latitude as Calgary, Canada. Oslo is at the same latitude as southern Alaska. Paris is further north than the northern tip of Newfoundland. The fact that these cities have the climates they have, mild, maritime, with growing seasons that support agriculture and winters that are cold but not subarctic, is primarily a consequence of the enormous heat transfer that AMOC performs. Remove AMOC, or significantly weaken it, and the climate of northwestern Europe does not simply become a bit cooler. It reorganizes fundamentally, shifting toward the continental cold that the latitude would otherwise dictate. Studies published in recent years have attempted to quantify what an AMOC collapse would mean for specific locations. A 2025 study in Geophysical Research Letters calculated that under a full AMOC collapse scenario, cold extremes in London could reach -20 degrees Celsius. In Oslo, -48. These are not the averages. They are the extremes that would become possible under the reorganized atmospheric circulation patterns that AMOC collapse would drive. But the impacts of AMOC weakening extend far beyond Europe. The heat that AMOC transports northward out of the tropics has a direct effect on the temperature gradient between the tropical Atlantic and the Sahara and Sahel regions of Africa, a temperature gradient that drives the West African monsoon. When AMOC weakens and less heat escapes the tropical Atlantic northward, the tropical Atlantic warms, the temperature contrast weakens, and the monsoon falters. This is not a theoretical effect. It is documented in the paleoclimate record with extraordinary clarity, as we will see when we examine the geological history of AMOC's past collapses. The connection between North Atlantic circulation and African rainfall is one of the most robust signals in the Deep Climate Archive, and it operates in exactly the direction that the physics predicts. A weaker AMOC means less rain in the Sahel and across large portions of West and East Africa. In a world where hundreds of millions of people depend on that rainfall for food, this is not an abstract concern. Then there is the sea level question. AMOC actively suppresses sea levels along the eastern coast of the United States by pulling water away from that coastline and driving it northeastward. When AMOC weakens, this suppression weakens too, and sea levels on the US Atlantic coast rise independently of the global mean sea level change driven by thermal expansion and ice melt. A 2025 study by US federal climate researchers found that the current's recent weak phase has already contributed to up to 50% of flooding events along the northeast coast of the United States since 2005. Not future flooding. Current flooding happening now, partly attributable to the AMOC weakening that the buoy data has been measuring since 2004. These effects, the European cooling, the African drought, the American coastal flooding, describe a system whose influence on human civilization is not peripheral, but fundamental. AMOC is not a climate curiosity. It is part of the infrastructure of the climate that modern civilization was built on. And before we look at what is happening to it now, we need to understand what has happened to it before. Because AMOC has a history, a geological history, documented in the sediment cores and ice cores and chemical proxies that paleoclimatologists have spent decades assembling. And that history is one of the most dramatic and informative records in the entire Earth Sciences archive. Before we examine the sedimentary record that documents these events, we need to pause on something that the geological literature tends to handle abstractly, but that deserves to be stated plainly. The Younger Dryas, the Heinrich Events, the Dansgaard-Oeschger cycles. These are not just climate signals in ice cores and sediment columns. They happened to people, real people, anatomically modern humans who were living in Europe and Asia and the Americas during these events, and who experienced their consequences not as isotopic excursions in a proxy record, but as the sudden, inexplicable deterioration of the world they had built their lives in. The human population of Europe during the last glacial maximum, roughly 26,000 to 19,000 years ago, the coldest phase of the last ice age, had retreated to a handful of refugia in southwestern Europe, primarily in what is now Spain, southern France and Italy, where the climate remained just barely viable for hunter-gatherer populations. As warming began after the glacial maximum, populations expanded northward, recolonizing the landscapes that ice had vacated. Pollen records from lake sediments across northern and central Europe show the northward advance of birch and pine forests, tracking the warming climate as trees colonized the freshly deglaciated ground. Archaeological sites from this period show human populations moving into new territories, establishing the rich and diverse Upper Paleolithic cultures, whose cave paintings we still marvel at. Then the Younger Dryas arrived. In terms of the pollen record, the signal is unmistakable and brutal. The temperate tree pollen, birch, pine, hazel, oak, disappears from the sediment sequences across northern and central Europe and is replaced by the pollen of tundra and steppe plants. Grasses, sedges, dwarf willow, Arctic herbs. The forest retreated south. The tundra advanced. Temperatures in Central Europe dropped by somewhere between 5 and 10 degrees Celsius in the space of a few decades. The growing season shortened. The game animals that hunter-gatherer populations depended on shifted their ranges southward or disappeared from regions they had recently recolonized. The archaeological record of the Younger Dryas in Europe is one of population contraction and cultural disruption. The Magdalenian culture, which had flourished across France and Spain and reached into Central Europe during the late glacial period, collapsed or transformed during the Younger Dryas. Settlement sites that had been occupied continuously for centuries were abandoned. Population densities, estimated from the density of archaeological sites in the record, declined sharply in the regions most affected by the cooling. Some researchers have argued that the Younger Dryas represents one of the most severe demographic contractions in European prehistory since the last glacial maximum itself, a reversal of the population growth and geographic expansion that the post-glacial warming had enabled, driven not by disease or warfare, but by the simple fact that the climate stopped cooperating. And it happened fast. The pollen records do not show a gradual transition over centuries. They show sharp boundaries, a layer where temperate forest pollen is abundant, then a layer where it is almost entirely absent, with very little gradual transition between them. This is what 10 degrees of cooling in a decade looks like in a biological record. An abrupt boundary in the sediment, a before and an after, with the transition between them compressed into a layer thin enough to be covered by a fingernail. The people who lived through it did not, of course, experience it as a geological transition. They experienced it as successive seasons that were colder than the last, as game becoming harder to find, as the forests they had relied on retreating southward faster than they could follow, as camps that had been viable becoming untenable. 1,200 years is a long time by human reckoning. It is roughly the interval between the fall of Rome and the European Renaissance. The Younger Dryas lasted that long. The European populations that survived it did so by retreating to refugia once again, compressing into the southern fringes of the continent, and waiting, generation after generation, for a warming that eventually came, but that no individual alive during the cold interval would live to see in its fullness. There is a particular irony in the timing of the Younger Dryas relative to the development of agriculture. The conventional dating of the agricultural revolution in the Fertile Crescent places its earliest manifestations at approximately 11,500 to 12,000 years ago, essentially concurrent with the end of the Younger Dryas and the resumption of Holocene warming. Some researchers have argued, and the evidence increasingly supports, that the attempts at plant cultivation that preceded the full agricultural revolution were disrupted or delayed by the Younger Dryas cooling and the associated weakening of the Levantine rainfall patterns that made wild cereal cultivation viable. The Natufian culture of the Eastern Mediterranean, which had been developing a proto-agricultural economy based on intensive wild cereal harvesting in the centuries before the Younger Dryas, showed evidence of contraction and stress during the cold interval, with sites being abandoned and populations shifting to more mobile subsistence strategies. When the Younger Dryas ended and the Holocene warmth resumed, the agricultural revolution followed within centuries. It is at least plausible that the 12,000-year delay between anatomically modern humans arriving in the Fertile Crescent and the development of agriculture there was, in part, a consequence of AMOC behavior. That human civilization is as old as it is in part because of when the conveyor last stopped and when it started again. This is what is at stake when we talk about AMOC. Not an abstract climate metric, not a percentage change in some quantity that most people have never heard of. The full history of what this circulation system does when it changes, written in the pollen of abandoned forests and the archaeological traces of retreating populations and the isotopic diaries of Greenland ice, is a history of how fundamentally and how rapidly the human world can be reorganized when the machine that runs it changes state. And that history is the context in which the current observational data must be read. The key to reading AMOC's past is understanding what it leaves behind when it changes. Like every major oceanographic process, AMOC inscribes its behavior into the sediments that accumulate on the ocean floor. The chemistry of the water column, its temperature, its oxygenation, the isotopic composition of the dissolved carbon dioxide it carries, changes when AMOC changes. And those chemical signatures are recorded by the tiny calcifying organisms called foraminifera that live in the water column, die, and sink to the seafloor. Their shells accumulate in the sediment in layers that preserve, like a chemical diary, the state of the ocean at the time of their death. By analyzing the isotopic composition of foraminifera shells at different depths in a sediment core, paleoclimatologists can reconstruct the history of ocean circulation with a precision that continues to improve as analytical techniques advance. What this record shows, for the last glacial period, the interval from roughly 115,000 years ago to 12,000 years ago, during which large ice sheets covered much of North America and Northern Europe, is a pattern of repeated, dramatic AMOC disruptions. The disruptions are called Heinrich Events, after the German oceanographer Hartmut Heinrich, who first described their sedimentary signature in a 1988 paper analyzing North Atlantic sediment cores. What Heinrich saw in his cores was a series of distinct layers of coarse-grained sediment, gravel and sand-sized particles, deposited in the open North Atlantic far from any land source. These coarse grains, which could not have been transported by ocean currents of normal strength, could only have arrived by one mechanism: iceberg rafting. They were rock debris frozen into icebergs that carved from the Laurentide ice sheet covering North America and drifted eastward across the North Atlantic, melting as they went and dropping their sediment load on the seafloor below. The coarse sediment layers that mark Heinrich Events are visible in North Atlantic sediment cores from Ireland to the Caribbean at roughly similar depths and therefore roughly similar ages, 6 times during the last glacial period at intervals of approximately 7 to 10,000 years. With the events labelled Heinrich I through Heinrich VI from youngest to oldest. Each layer represents an episode of massive iceberg discharge into the North Atlantic, an armada of ice carrying fresh water from the North American ice sheet into the ocean, diluting the salty, dense surface waters of the North Atlantic and disrupting the density-driven sinking that keeps AMOC running. The freshwater input from Heinrich Events was enormous. Estimates of the freshwater flux associated with the largest Heinrich Events reach several tenths of a sverdrup sustained over centuries, small compared to the volume of AMOC itself, but strategically targeted at exactly the locations where North Atlantic deep water forms. Freshwater is less dense than saltwater. Add enough fresh water to the surface of the North Atlantic and the surface layer becomes too light to sink, regardless of how cold it gets. The thermohaline conveyor stalls, AMOC, weakens dramatically, in some events possibly collapsing to near zero, and the climate of the Northern Hemisphere reorganizes accordingly. The paleoclimate record of Heinrich Events reads like a script for what a major AMOC disruption does to the world. Sea surface temperatures in the North Atlantic cooled by 5 to 10 degrees Celsius in decades. Air temperatures over Greenland, reconstructed from ice core records, dropped by as much as 15 degrees within decades of each Heinrich event onset. European climate deteriorated severely, with cold, dry conditions replacing the relatively milder periods between events. And in the tropics, the monsoon systems shifted. The intertropical convergence zone, the band of tropical rainfall that follows the warmest surface waters, migrated southward as the North Atlantic cooled, bringing drought to the regions that normally receive its rainfall and anomalous precipitation to regions that are normally dry. The record of these tropical shifts is preserved in cave deposits called speleothems, whose oxygen isotopic composition records the amount and source of rainfall above the cave in lake sediments across the tropical Americas and Africa and Asia, and in the pollen records of terrestrial ecosystems that show dramatic vegetation changes in response to the altered rainfall patterns. What the Heinrich event record establishes with clarity is that AMOC disruption is not a gradual, gentle process. The transitions are fast. The Greenland ice core records, which have annual layer resolution for much of the last glacial period, show temperature changes of 10 to 15 degrees Celsius occurring within decades, sometimes within years. The climate system has a threshold character, a bistability that paleoclimatologists have been documenting and theorizing about for decades. There is not a smooth continuum of AMOC strengths, with the climate responding proportionally to each incremental change. There are two preferred states, a strong circulation mode and a weak or absent circulation mode, and the system tends to reside in one or the other rather than in intermediate states. Transitions between them, when they occur, are therefore abrupt. A gradual forcing, gradual freshwater input, gradual warming can push the system toward the threshold for a long time with relatively muted response, and then the threshold is crossed, and the system snaps from one state to the other in decades or centuries. This bistability is not a hypothesis. It was demonstrated in a simple box model of ocean circulation by Henry Stommel in 1961, has been reproduced in climate models of every level of complexity since, and was confirmed most recently in a high-resolution ocean model by a Dutch research group whose 2025 paper by Van Westen and colleagues showed the tipping point in an eddy-resolving ocean model, the most physically realistic type of simulation available, for the first time, removing the last serious argument that the bistability might be an artifact of simplified models. The most recent major AMOC disruption before the present era is the Younger Dryas. It is the best documented and the most consequential for human history, because it occurred at the end of the last ice age, during the period when modern humans were recolonizing Europe after the glacial maximum and developing the agricultural economies that would eventually give rise to civilization. Approximately 12,900 years ago, during a period of warming and rapid ice sheet retreat following the end of the last ice age, AMOC disrupted again. The mechanism, as now understood, involved the catastrophic drainage of meltwater into the North Atlantic, the most likely route being via the Mackenzie River system in what is now northwestern Canada, rather than the St. Lawrence as originally proposed, delivering an enormous pulse of fresh water that stalled the thermohaline conveyor. The result was one of the most dramatic climate reversals in the geological record of the Holocene and the late Pleistocene. Within decades, temperatures in the North Atlantic region and across Europe plummeted. Greenland ice cores record a temperature drop of approximately 10 to 15 degrees Celsius within the span of a decade or less. The warming that had been underway for thousands of years went into reverse. Tundra and steppe vegetation replaced the forests that had been spreading northward across Europe. Glaciers that had been retreating advanced again. The Younger Dryas stadial, as the cold interval is formally known, lasted approximately 1,200 years, from 12,900 to 11,700 years ago, before AMOC resumed and the warming continued. Research published in Science Advances in early 2026, analyzing biomarker records from the Labrador Sea and eastern Baffin Bay, revealed that the Younger Dryas was not a simple single AMOC off event. The circulation actually underwent a two-phase pattern. An initial collapse driven by the meltwater pulse, a partial recovery mid-Younger Dryas, as sea ice retreated and Atlantic water flowed back in, and then a second weakening as that warm water influx destabilized sea ice and caused surface freshening that drove a second AMOC decline in the late Younger Dryas. The system oscillated even during the cold period, responding to feedbacks and perturbations that cascaded through the climate system in ways that are only now being understood at this level of detail. And then, approximately 11,700 years ago, AMOC recovered fully and the Holocene began. The geological evidence for this recovery is as dramatic as the evidence for the collapse. Temperatures in Greenland rose by 10 degrees within 50 years. The tundra retreated. Forests advanced northward. The monsoons strengthened. Sea levels rose as ice sheets melted in the renewed warmth. The world that modern human civilization was built on, the relatively warm, relatively stable climate of the past 12,000 years, is in large part a consequence of AMOC having been in its strong operational mode continuously since the end of the Younger Dryas. The 12,000-year baseline was quantified for the first time in a study published in August of 2025 by researchers from Heidelberg University and the University of Bern. Using geochemical analyses of marine sediments, they reconstructed the strength of AMOC over the entire Holocene, the 12,000 years of the current interglacial, and produced the first quantitative estimate of how the circulation has varied through this interval. Their findings showed that after a period of recovery following the Younger Dryas, AMOC stabilized at approximately 18 sverdrups around 6,500 years ago and remained broadly stable at that level through most of the mid and late Holocene, with natural fluctuations, but no catastrophic disruptions. 18 sverdrups. That number is the baseline. The level at which AMOC has been operating for most of the 12,000 years of recorded human civilization. The level against which current measurements must be compared. Before we turn to what the instruments have been measuring, we need to examine the forcing that is currently being applied to the system, the mechanism by which human activity is perturbing the thermohaline machine in a way that parallels, with uncomfortable precision, the natural forcing that drove the Younger Dryas and the Heinrich Events. The Laurentide ice sheet that covered North America during the last ice age was the primary source of the fresh water that disrupted AMOC during the Heinrich Events and the Younger Dryas. It has been gone for roughly 8,000 years, but there is another ice sheet that has not gone anywhere yet, that is losing mass at an accelerating rate, and that is positioned directly adjacent to the formation zones of North Atlantic deep water, where AMOC's sinking branch operates. That ice sheet is Greenland. The Greenland ice sheet holds approximately 2.85 million cubic kilometers of ice, enough, if it melted entirely, to raise global sea levels by approximately 7 meters. It is not going to melt entirely on any timescale relevant to the current discussion. But it does not need to melt entirely to disrupt AMOC. It needs only to discharge enough fresh water into the surrounding ocean to dilute the surface salinity of the Labrador Sea and the Nordic Seas, the two primary formation regions for North Atlantic deep water, below the threshold where dense enough water forms to sink and sustain the overturning circulation. Current estimates of Greenland ice mass loss are unambiguous and trending in one direction. The ice sheet is losing approximately 280 billion tons of mass per year. averaged over the past 2 decades, with significant year-to-year variability, but a clear long-term upward trend in the rate of loss. This mass is lost through 2 mechanisms: surface melt, in which warmer air temperatures melt ice that then flows as liquid water to the ocean, and dynamic discharge, in which outlet glaciers accelerate and carve icebergs directly into the ocean. Both are increasing. Both deliver fresh water to exactly the regions of the North Atlantic where its effect on AMOC density is most potent. The Labrador Sea is particularly critical. It is one of the 2 primary sites of deep water formation in the North Atlantic, located between Greenland and the Canadian Maritime Provinces, and it receives freshwater discharge from Greenland's western outlet glaciers directly. The Jakobshavn Glacier, which drains approximately 7% of the Greenland ice sheet and is one of the fastest-moving glaciers in the world, discharges into Disco Bay, a body of water that feeds directly into the Labrador Sea. The fresh water from Jakobshavn and the other western Greenland outlet glaciers reduces the surface salinity of the Labrador Sea, making the surface water less dense and therefore less prone to the convective sinking that drives AMOC. This is the same mechanism, operating in the same location, that drove the AMOC disruption at the Younger Dryas onset, a reduction in surface salinity in the Labrador Sea through freshwater influx that suppressed deep water formation. The difference is rate and predictability. The meltwater pulse that initiated the Younger Dryas was a catastrophic, essentially instantaneous geological event, a drainage of a proglacial lake that delivered an enormous volume of fresh water to the ocean over a period of decades to centuries at most. The current Greenland freshwater forcing is slower in absolute terms, but is accelerating in a way that makes the long-term trajectory deeply concerning. The rate of Greenland mass loss has been increasing decade by decade. The 2000s were worse than the 1990s. The 2010s were worse than the 2000s. Preliminary data for the current decade suggests the acceleration is continuing. The models that project future AMOC behavior have, until very recently, used Greenland melt estimates that are based on relatively conservative ice sheet dynamics. They do not fully account for the marine ice sheet instability mechanisms that could accelerate Greenland mass loss significantly beyond current rates. This is why Stefan Rahmstorff of the Potsdam Institute has repeatedly cautioned that the IPCC projections for AMOC change are likely to be underestimates, because the models undercounting the Greenland forcing will also undercount the AMOC response. There is also the question of what happens to the fresh water once it enters the ocean. It does not distribute uniformly across the global ocean. It accumulates preferentially in the subpolar North Atlantic, in the Labrador Sea and the seas around Greenland, where it creates a freshwater lens at the surface that inhibits convective sinking. The century-old cold blob in the subpolar North Atlantic is in part a manifestation of this freshwater accumulation. The surface layer has become fresher and therefore less able to lose heat by sinking, which means it retains heat less efficiently and runs colder than the surrounding ocean. It is a self-reinforcing pattern. fresher water forms a more stable surface layer. The stable surface layer suppresses deep convection. The suppressed convection weakens AMOC. The weakened AMOC brings less warm salty water from the south to replenish the surface layer, which becomes even fresher. The geological record of the Heinrich Events shows exactly this kind of feedback amplification. An initial freshwater perturbation that is amplified by internal feedbacks until the system crosses the bistability threshold and collapses. One more aspect of the Greenland forcing deserves attention because it distinguishes the current situation from the natural Holocene variability that the Heidelberg 12,000-year reconstruction documented. The natural AMOC fluctuations of the Holocene, the weakening around 9,000 to 8,000 years ago that the Heidelberg study identified, the various multi-decadal variability patterns that have characterized the modern instrumental record, occurred against a background of broadly stable Greenland mass balance. The ice sheet was neither gaining nor losing mass at any alarming rate for most of the Holocene, and the freshwater forcing on the North Atlantic was correspondingly stable. The current situation involves an ice sheet that is losing mass at a historically unprecedented rate. In the context of the past 12,000 years, delivering fresh water to the critical formation zones of North Atlantic deep water faster than at any point in the Holocene record, and accelerating. This is not natural variability. This is a novel forcing, and the geological record provides no close analog for its combination of rate and location. Current measurements. The rapid array, installed at 26.5 degrees north latitude and running since 2004, has now accumulated more than 20 years of continuous AMOC monitoring data. It is the longest and most comprehensive direct observational record of AMOC strength in existence. Analysis of the rapid data published in 2026 by Xing and colleagues found a decline of 2.6 sverdrups per decade over the 2004 to 2023 period, from 20 sverdrups at the beginning of the record to 15 sverdrups at its end, from 20 to 15 in 20 years, against a Holocene baseline of 18. Let that comparison register. The 12,000-year baseline established by the Heidelberg study is 18 sverdrups. The current value, as measured by the most comprehensive direct observational program ever applied to AMOC, is 15. The system is already operating below its Holocene baseline, and it has been declining at 2.6 sverdrups per decade for at least 20 years. The May 2026 study from the University of Miami Rosenstiel School confirmed and extended this picture. Researchers analyzed data from 4 mooring arrays along the western boundary of the North Atlantic, at multiple latitudes rather than just the rapid array's single latitude, and found meridionally consistent weakening at all 4 locations. This is significant because AMOC is a 3-dimensional circulation, and a weakening trend observed at multiple latitudes simultaneously is much harder to attribute to regional variability or natural fluctuation than a single-site trend. The western boundary is, as the study's lead author Shane Ellipott described it, the canary in the coal mine for what's happening to the overall circulation. And the canary has been singing the same note at 4 different heights since 2004. The Companion Science Advances study, published at the same time in April of 2026, took a different approach. Rather than examining the observational record alone, researchers combined the mooring data with climate model projections, using the real-world observations to constrain which models are most realistic, a technique called observational constraint. The result was sobering. Once the models are filtered to retain only those consistent with the observed rate of AMOC decline, the projected future weakening becomes significantly more severe than the unconstrained model ensemble suggests. The constrained projections show AMOC weakening by 51% by 2100 under a medium emissions scenario. That would take the system from its current 15 sverdrups to approximately 7 or 8. To put that in context, it would place AMOC at levels approaching those seen during the Heinrich Events of the last ice age, when the Northern Hemisphere climate reorganized dramatically and European temperatures dropped by 10 to 15 degrees. The Bistability question is where this observation data intersects with the most alarming theoretical work. In 2026, a comprehensive review study assessed the evidence base for AMOC bistability, the property that would allow the system to tip abruptly from its current operational state to a collapsed state rather than declining gradually. The review concluded that the evidence base for bistability had broadened considerably in recent years, and that the present-day AMOC was operating in a bistable regime. What bistability means practically is this: there is a threshold, somewhere between the current state and full collapse, below which the system cannot sustain itself and tips irreversibly into the collapsed mode. The location of that threshold is uncertain. This is one of the most consequential unknowns in current climate science. But the evidence increasingly suggests it exists, and that the current direction of travel is toward it. An April 2026 opinion piece published in the European Geosciences Union Journal, co-authored by Stefan Rahmstorff of the Potsdam Institute, one of the scientists who has studied AMOC dynamics for longer and more thoroughly than almost anyone, argued explicitly that the accumulated evidence base now requires taking the AMOC weakening signals seriously as a genuine trend rather than natural variability. Rahmstorff noted that the models showing the most pessimistic AMOC forecasts, models that had been criticized as unrealistically pessimistic, are, when constrained by the observational data, the most realistic ones. The optimistic models, which showed minimal AMOC change, do not match what the buoys have been measuring. The pessimistic models do. The instruments in the North Atlantic have only been operating since 2004. 20 years of direct measurements is an extraordinary scientific achievement. It was essentially nothing before RAPID was deployed. But it is a short record compared to the multi-decadal to centennial scales on which AMOC naturally varies. And the question of whether the observed decline represents a genuine forced trend or a natural fluctuation that happens to have lasted 20 years is one that the mooring data alone cannot fully resolve. For that question, we need longer records, and as it turns out, we have them, though they require some ingenuity to read. The cold blob is one of the most unusual features in the modern sea surface temperature record of the North Atlantic. While virtually every other part of the global ocean has warmed over the past century in response to greenhouse gas forcing, a roughly oval region of the subpolar North Atlantic, centered approximately south of Iceland and southeast of Greenland, has cooled, not failed to warm as much as the rest of the ocean, actually cooled in absolute terms relative to its early 20th century baseline. This cooling anomaly has been present, to varying degrees, since at least the 1990s in the modern instrumental record. But when researchers extended the analysis backward using historical ship-based sea surface temperature measurements, they found that the cold region had been present intermittently since the early 20th century and had become more persistent and more pronounced since the 1970s. The cold blob was noticed and described in multiple studies over the years, but its cause was debated. Was it a regional oceanographic phenomenon, a consequence of atmospheric circulation changes, a response to aerosol forcing from European industrial emissions that had suppressed regional temperatures through the mid-20th century? All of these hypotheses had some support from different lines of evidence, and the debate remained unresolved for years. In December of 2025, a study published and reported in Science Daily finally connected the cold blob definitively to AMOC. The research showed that the spatial pattern and temporal evolution of the cold blob, its location, its intensity, its timing, is consistent only with a long-term slowdown in AMOC, specifically with the reduction in northward heat transport that a weakening overturning circulation would produce. The cold blob marks the region where AMOC normally deposits large amounts of heat from the tropical Atlantic, the endpoint of the northward heat transport, where warm water loses its heat to the atmosphere and sinks. When AMOC weakens, less heat arrives at this location. The sea surface cools and the cold blob appears. The study found that only climate models incorporating a weakened AMOC matched the observed cold blob pattern. Models without AMOC weakening could not reproduce it, regardless of what other climate forcings were included. The significance of this finding extends beyond confirming what the buoy data had already suggested. It provides a longer duration signal for AMOC weakening, a signal visible in sea surface temperature records going back over 100 years, that is independent of the direct circulation measurements. When two fundamentally different types of observations, using fundamentally different measurement approaches over fundamentally different time periods, converge on the same conclusion, the confidence in that conclusion rises dramatically. The buoys say AMOC has been declining since 2004. The cold blob says AMOC has been declining since at least the mid-20th century and possibly since the early 20th century. The mid-depth Atlantic warming signal, documented in the 2025 study, that analyzed temperature changes at depths of 1,000 to 2,000 meters since the 1960s, adds a third independent line of evidence pointing to the same multi-decadal trend. This convergence of evidence from different sources and different timescales is what separates the current AMOC situation from a simple 20-year observational anomaly. The story that these independent datasets tell is consistent. The overturning circulation has been losing strength over a period measured not in decades, but in half-centuries to a century. The rate of decline may be accelerating. The buoy data, which covers the most recent 2 decades, shows a steeper rate of change than the longer-term proxy-based reconstructions. But the trend has been present for longer than most people realize, embedded in the century-scale temperature record of the North Atlantic, waiting for researchers to read it correctly. There is one more aspect of the cold blob story that connects the present to the geological past in a particularly striking way. The formation of the cold blob is precisely what the paleoclimate models predict should occur in the early stages of an AMOC weakening, a cooling of the subpolar North Atlantic as northward heat transport decreases before the more dramatic climate impacts of a major AMOC disruption develop. In the geological record of past Heinrich Events, there is a documented precursor signal in North Atlantic sediment cores, a cooling and freshening of the surface ocean in the subpolar region that precedes the full Heinrich event by decades to centuries. This precursor signal is, in effect, the paleo equivalent of the cold blob, the early warning that the system is being perturbed. The research published in Nature Communications showing that subsurface ocean warming preceded Heinrich events by 1 to 2,000 years identified a similar precursor dynamic operating on longer timescales. The implication is that the system provides warning signals before it crosses the threshold, signals that are visible in the right proxies if you know where to look. The cold blob is visible. We are looking at it. What it is telling us is that the precursor dynamics that the geological record associates with AMOC disruption are already underway. There is one more piece of the scientific picture that deserves particular attention, because it addresses a question that tends to arise in discussions of AMOC, and that has sometimes been used to minimize the concern. Is the current AMOC weakening really caused by human activity, or is it just natural variability? The mooring data alone cannot definitively answer this question. 20 years is a relatively short record compared to the multi-decadal to centennial timescales of natural AMOC variability. And distinguishing a forced anthropogenic trend from a natural fluctuation in a 20-year record requires additional lines of evidence. Those additional lines of evidence are substantial, and they converge. The cold blob, the mid-depth Atlantic warming, the mooring data. 3 independent instruments, 3 different timescales, 1 conclusion. Then there are the mid-depth temperature changes in the tropical Atlantic. A study published in 2025 found that mid-depth warming in the Atlantic at depths between 1,000 and 2,000 meters, a predicted consequence of AMOC slowdown that acts as a more stable long-term indicator than surface proxies, has been increasing robustly since the 1960s and emerged from natural variability in the early 2000s, consistent with an AMOC forced signal rather than natural fluctuation. Now we need to visit one more geological archive, because it offers a perspective on the current situation that neither the observational data nor the model projections alone can provide. In September of 2025, a paper published in Geophysical Research Letters reported the results of simulations with a fully coupled Earth system model examining the role of orbital forcing in past AMOC collapses. What the researchers found was remarkable. Without adding any fresh water to the ocean, without iceberg discharge, without meltwater pulses, without any of the ice sheet-related forcings that are typically invoked to explain past AMOC disruptions, a complete AMOC collapse could be achieved through orbital forcing alone. Specifically, through the Earth's axial precession, the slow wobble in the orientation of Earth's rotational axis that cycles over approximately 26,000 years and affects the seasonal distribution of solar radiation, reaching the high latitudes of the northern hemisphere. Under the right orbital configuration, high eccentricity, with Earth furthest from the Sun at summer solstice in the northern hemisphere. The reduction in northern hemisphere summer insolation was sufficient in the model to weaken AMOC gradually over thousands of years until it crossed the Bistability threshold and collapsed abruptly. No freshwater forcing required. The orbital geometry alone was sufficient. The implication of this finding is that AMOC has been collapsing periodically throughout the Pleistocene, not just during the Heinrich Events driven by ice sheet instability, but as a response to the fundamental orbital cycles that have paced glacial and interglacial periods for millions of years. The conveyor has been stopping and starting for as long as the current geometry of the Atlantic Ocean has existed, which is to say, for tens of millions of years. This is not a rare or unusual event in geological terms. It is a recurring feature of the climate system, as normal as the advance and retreat of ice ages. What is unusual about the current situation is not that AMOC might slow or stop. It is that the forcing driving the current slowdown is not an orbital cycle operating over tens of thousands of years, not a meltwater pulse from an ice age ice sheet, but a change in atmospheric chemistry occurring over 2 centuries. A change of unprecedented speed in the context of any previous AMOC disruption in the geological record. The speed matters for the same reason that speed always matters in the context of climate change. Ecosystems, species, human societies all have some capacity to adapt to change. But that capacity is finite and scale-dependent. A change that takes 10,000 years allows forests to migrate, species to evolve, peoples to move. A change that takes decades or centuries compresses the adaptation window to a fraction of what evolution or ecology or social reorganization can accomplish. The previous AMOC disruptions were fast by geological standards, decades, not millennia, but they were driven by natural forcings that are now well understood and that have no equivalent in the current situation. The question that every serious researcher in this field eventually confronts and that every honest discussion of AMOC must address directly is the threshold question. Where is the point of no return? Below what level of AMOC strength does the Bistability kick in and the system begin an irreversible transition to a collapsed state? And how close are we to it? The honest answer to the first part of this question is that we do not know precisely. The threshold is model dependent, and different models place it at different levels of AMOC strength. The bistability itself, the existence of two stable states between which the system can transition, is now robustly established across the full spectrum of model complexity, from Stommel's original two-box model to the high-resolution eddy-resolving simulations of Van Westen and colleagues published in 2025. But the specific AMOC strength below which the system cannot sustain itself and begins an irreversible decline is an uncertain quantity, sensitive to the detailed representation of ocean mixing, salinity feedbacks, and atmospheric coupling in any given model. The uncertainty range spans from roughly 10 to 5 sverdrups in different studies, a range that, given the current measured value of 15, means the threshold could be relatively close or could be somewhat further away than the current trajectory implies. A 2024 study from the University of Copenhagen attempted to constrain this uncertainty using statistical methods applied to the observational record of AMOC variability. The study, which analyzed the time series behavior of AMOC proxies over the past century, looking for the kind of statistical precursors, slowing of recovery from perturbations, increased variance, that systems approaching a threshold tend to exhibit, concluded with 95% confidence that an AMOC collapse could occur between 2025 and 2095. The central estimate was a collapse occurring around 2057. This result was widely reported and widely contested. The statistical methodology, critical slowing down analysis, is well established in the theory of tipping elements, but is sensitive to the quality and resolution of the input data, and several researchers challenged whether the available AMOC proxy data was adequate for the approach. The debate has not been fully resolved, but the Copenhagen study does represent a serious attempt by serious researchers to put numbers on the threshold question, using the available data, and its central estimate of mid-century falls within a range that is consistent with the Dryas and colleagues' 2025, finding that AMOC declined to 10 sverdrups, implied by the current trajectory continued at its present rate for roughly another 2 to 3 decades, would place the circulation on a path toward full shutdown according to the CMY P6 model ensemble. The current 15 sverdrups represents a system that has already declined by a quarter from its Holocene baseline of 20 sverdrups measured at the start of the rapid record, or by approximately 17% from the 12,000-year Holocene average of 18. The April 2026 Science Advances study, using observational constraints on the model ensemble, projects a further decline to approximately 7 to 8 sverdrups by the end of this century, under a medium emissions scenario, representing a total weakening of more than 60% from the early rapid baseline. At that level, according to the Dryas analysis, the CMIP6 models suggest the circulation would be approaching the threshold below which full shutdown becomes a realistic trajectory. This does not mean collapse is inevitable, but it means the trajectory that the constrained models project would, by the end of this century, bring AMOC into a range where the bistability threshold becomes a near-term concern rather than a distant one. There is an important distinction to make here between a partial weakening of AMOC, which has significant climate consequence, but does not involve the abrupt state transition of a full collapse, and the Bistability threshold crossing that would represent a qualitatively different and potentially irreversible change. Much of the climate impact described in the previous section, the European agricultural impacts, the African monsoon weakening, the US coastal sea level rise, would manifest at levels of AMOC weakening that fall short of full collapse. The system does not have to cross the Bistability threshold for its weakening to have serious consequences. The geological record of the Holocene itself includes intervals of AMOC weakening that caused measurable climate impacts without rising to the level of a full Heinrich-style collapse. The current weakenings already producing measurable impacts: the flooding on the US northeast coast, the long-term cooling trend in the cold blob region. The question of whether the system will eventually cross the threshold into abrupt collapse is separate from, and more uncertain than, the question of whether it will continue to weaken in ways that produce increasing climate disruption. The distinction between a gradual weakening and an abrupt collapse matters enormously for how societies should respond to the current situation. But it is important not to let the uncertainty about the threshold become a reason to discount the certainty about the trend. The trend is measured. It is documented. It is confirmed by multiple independent lines of evidence across multiple timescales. The AMOC is currently operating below its Holocene baseline and has been declining for at least 20 years by direct measurement and for several decades to a century by proxy evidence. Whether it eventually crosses the bistability threshold into abrupt collapse or merely continues declining to a new, weaker state that still carries major climate consequences, either outcome represents a departure from the climate that human civilization was built on. The geological record does not offer a version of this story in which significant AMOC weakening produces acceptable climate outcomes. What it offers is a range of outcomes from bad to very bad, depending on how far and how fast the system declines and whether the threshold is crossed. What the current science cannot tell us, and what the geological record similarly cannot tell us, is exactly when or whether the threshold will be crossed. The uncertainty is real, and it should be acknowledged honestly. But uncertainty about the timing of a potential threshold crossing is not the same as uncertainty about whether the threshold exists. Uncertainty about whether the system is heading in the wrong direction or uncertainty about what happens on the other side. On all three of those questions, the existence of the threshold, the direction of travel, and the consequences of crossing it, the evidence is considerably less uncertain than the popular discussion of AMOC often implies. The threshold exists. The system is heading toward it. The geological record of what has happened every previous time a major AMOC disruption occurred is one of the most thoroughly documented bodies of evidence in the earth sciences. The difference between the current situation and every previous AMOC disruption in the geological record is not the direction of change or the potential consequences. It is the presence, for the first time, of a civilization capable of measuring the change, understanding the mechanisms, modeling the consequences, and, in principle, altering the forcing that is driving it. Whether that capability translates into action of sufficient scale and speed to make a difference to the AMOC trajectory is a question that sits outside the domain of geology and oceanography. It sits in the domain of human decision-making, operating on a timescale that is short relative to the geological processes involved, but that may still be adequate, if used well, to influence the outcome. The geological record of those previous disruptions also tells us something about what recovery looks like and how long it takes. The Younger Dryas lasted 1,200 years. The Heinrich Events, while variable in their duration, maintained cold conditions for centuries to a millennium. Recovery of AMOC after the Younger Dryas, as modeled in the 2025 trace simulation, involved a two-phase process that took centuries after the freshwater forcing ceased. The implication is that even after the forcing that is currently driving AMOC weakening, the influx of fresh water from Greenland melting, the warming of the subpolar North Atlantic, is eventually removed or stabilized. The recovery of AMOC to its Holocene baseline strength would likely take decades to centuries, not years. The climate impacts during that recovery period would be persistent and pervasive. The numbers that climate scientists use to describe AMOC change, sverdrups, percentage declines, temperature anomalies in degrees Celsius, are precise and useful, but they have a tendency to abstract the reality of what they describe. Before we arrive at the final reckoning, it is worth translating those numbers into the terms that actually govern human life. Food, water, the capacity of the land and the rain to sustain the populations that depend on them. Europe is the most obvious case, because the AMOC climate connection there is most direct and most extensively studied. Northwestern Europe, the British Isles, Scandinavia, France, Germany, the Low Countries, owes its agricultural productivity to a combination of adequate rainfall and a growing season long enough to mature the crops that feed its populations. Both are consequences, in significant part, of AMOC. The maritime climate of northwestern Europe, mild winters, cool summers, reliable year-round precipitation is what it is because of the continuous delivery of heat from the North Atlantic, which keeps winter temperatures higher than the latitude would otherwise dictate, and maintains the atmospheric circulation patterns that bring westerly winds and precipitation off the ocean. Reduce AMOC significantly, and both of these conditions change. The winters become colder and more continental in character, with more frequent extreme cold events, hence the geophysical research letters finding of potential -20 Celsius extremes in London and -48 in Oslo. Growing seasons shorten as spring arrives later and autumn frosts arrive earlier. Crop yields decline not just because of lower average temperatures, but because of increased variability, the unpredictable extremes that become more frequent when the oceanic thermostat that moderates the climate is weakened. Wheat, barley, and oilseed rape, the primary arable crops of northwestern Europe, are all sensitive to late spring frosts and shortened growing seasons. A reduction in the length of the European growing season by several weeks would have measurable and significant impacts on yields in the major agricultural regions of the UK, France, and Germany, which together account for a substantial fraction of European food production. But the European agricultural impact, serious as it would be, is arguably not the most consequential food security consequence of a major AMOC disruption. That distinction belongs to the African monsoon. The West African monsoon, which delivers the majority of annual rainfall to the Sahel, West Africa, and the Guinea coast, is driven by the differential heating between the tropical Atlantic and the African landmass. When AMOC weakens and carries less heat northward, the tropical Atlantic warms relative to its normal state. The heat that would normally be exported northward accumulates instead in the tropical ocean. This warming of the tropical Atlantic changes the temperature gradient that drives the monsoon circulation, weakening the moisture flux onto the continent and shifting the rainfall belt southward, away from the regions that most depend on it. The Sahel, the semi-arid zone stretching across Africa from Senegal to Sudan, immediately south of the Sahara, is acutely sensitive to even small changes in monsoon rainfall. The devastating Sahel droughts of the 1970s and 80s, which caused widespread famine and contributed to major political instability across the region, are now understood to have been partly driven by changes in Atlantic sea surface temperatures that affected monsoon circulation. Changes that are consistent with the kind of AMOC fingerprint that the cold blob represents. More than 300 million people live in the Sahel and surrounding regions. Their food security depends on a monsoon whose behavior is directly linked to the state of a circulation system that is currently operating below its Holocene baseline. The Indian subcontinent adds another dimension to this picture. While the Indian summer monsoon is driven primarily by the temperature differential between the Indian Ocean and the Asian landmass, it is not isolated from the global atmospheric circulation patterns that AMOC influences. Paleoclimate records from Indian cave deposits Speleothems, whose oxygen isotopic composition records monsoon rainfall going back thousands of years, show a clear correlation between North Atlantic climate events and Indian monsoon strength. During Heinrich Events, when AMOC collapsed and the North Atlantic cooled dramatically, the Indian monsoon weakened simultaneously. The mechanism involves the Intertropical Convergence Zone, the global band of tropical convection that migrates with the seasons. When North Atlantic cooling shifts the ITCZ southward. In the Atlantic sector, the displacement propagates through the global atmosphere, affecting monsoon systems from West Africa to South Asia. 1.5 billion people depend on the Indian monsoon. The connection between their rainfall and the state of a circulation system in the North Atlantic is documented in the geological record with sufficient clarity that it should not be dismissed as a theoretical concern. And Boston, New York, and Miami are not waiting for the future impact. The 50% of flooding events already attributable to AMOC weakening since 2005 is not a projection. It is infrastructure damage already paid for, insurance claims already filed, streets already flooded. The machine has not stopped. It has slowed. And even at 15 sverdrups, the invoice is already arriving. It would be a mistake, however, to present these consequences as inevitable or already determined. The current measurements show AMOC at 15 sverdrups, below its Holocene baseline of 18, declining at 2.6 sverdrups per decade, but not yet at the levels associated with the most severe climate reorganizations of the past. The gap between where the system is now and where the geological record shows catastrophic impacts beginning is not zero. It is a gap that may still be influenced by the trajectory of greenhouse gas emissions and the rate of Greenland ice loss. The difference between a world that stabilizes AMOC at 12 sverdrups, slow, impactful, but not catastrophic, and a world that allows it to cross the Bistability threshold into near collapse, is not determined. The geological record documents what happens at each of those outcomes. The choice between them is still, in some meaningful sense, available. Now let me tell you what I think about this, as someone who has spent time with the full body of evidence that the geological record and the observational program have assembled, and who tries to think about it without the motivated reasoning that tends to afflict both the most alarmed voices and the most skeptical ones. I think the most important fact about the current AMOC situation is also the most underappreciated one. It is not the future projections, alarming as they are. It is the observation that the system is already operating below its Holocene baseline, not approaching the baseline from above and potentially threatening to breach it, already below it. The baseline that characterized the 12,000 years of stable climate during which everything we call civilization was built, the agriculture, the cities, the trade networks, the accumulated knowledge, the population growth, that baseline was 18 sverdrups. The current measurement is 15. Something has already changed. not in a model, not in a projection, in the actual ocean, measured by instruments, confirmed by multiple independent lines of evidence across multiple timescales. The second thing I think about is the bistability. The geological record is extremely clear that AMOC does not weaken gradually and smoothly. It thresholds. It lives in one of two states and jumps between them. The Younger Dryas was not a slow cooling. It was a snap. Greenland temperatures dropped 10 degrees in a decade. The transition from the Younger Dryas back to the Holocene was equally abrupt. The system does not give you a gradual warning proportional to how close you are to the threshold. It gives you a gradual approach and then a discontinuity. This property of the system, documented in the paleoclimate record, demonstrated in models from the simple to the most complex, and recently confirmed in the high-resolution Van Western simulations, means that the current rate of weakening may not be an accurate guide to how much time remains before something more dramatic occurs. The system can weaken for a long time without tipping and then tip. The third thing, and I think this is the one that the geological record most insistently teaches, is the difference between Earth recovering and the world we built recovering. The Earth will be fine. AMOC has collapsed before. The climate reorganized, the circulation eventually resumed, and the biological world adapted over centuries and millennia. None of that is in question. What is in question is whether the specific climate that modern human civilization was built on, the stable, warm, productive climate of the Holocene, with its reliable monsoons and its mild European winters, and its predictable agricultural seasons, can be maintained in a world where the circulation that largely creates that climate is operating below its Holocene baseline and declining. The geological record says that when our MOC changes significantly, the climate changes significantly and then stays changed for a long time. The present observations say that AMOC is already below its Holocene baseline. The connection between those two facts is not a model. It is not a projection. It is the direct application of what we know from the geological past to the measurements we are taking in the present. And what it says is this: the machine that runs the world's climate is running more slowly than it has for 12,000 years. The geological record of what has happened every previous time it slowed down this much is one of the most thoroughly documented and most consistently alarming records in the entire Earth Sciences archive. And we are the first civilization in 12,000 years of human history to watch it happening in real time, with instruments precise enough to measure the change, and with the accumulated knowledge of the geological past to understand what it means. That is not doom. That is information. The most important kind of information we have access to. Information from the deep past that tells us what the future looks like when the physics runs in the direction it is currently running. The geological record does not vote. It does not advocate. It simply records what happened last time. And last time, it took centuries to recover. The conveyor that runs the world has run before. It has stopped before. And it has started again, always, so far, eventually. What the sediments preserved from those previous interruptions cannot tell us is what the world looked like to the people who lived through them. What 1,200 years of Younger Dryas climate felt like to the humans trying to farm across a Europe that was returning to near glacial conditions. The geological record preserves the chemistry of the change. It does not preserve the weight of it. We are the first generation with the instruments to measure the change before it arrives. That is an extraordinary privilege and an extraordinary responsibility. The buoys in the North Atlantic have been speaking clearly for 20 years. The question is whether we are listening.